Ohm's law. See, when a conductor is connected to a cell provides the terminal potential difference across the ends of the conductor. It creates potential difference so that electric field will develop inside the conductor. That electric field drives the electrons in one direction. Okay. So, the amount of flow of current in a conductor is directly proportional to terminal potential difference across the conductor, and the proportionality is replaced with some constant, say 1 by R into V. So, V is equal to IR. Okay. Ohm's law is stated as the electric current flowing through a conductor is directly proportional to potential difference between the ends of the conductor, provided physical state of the conductor remains unchanged. That means temperature, all these things must be remains same, and this wire is a solid in nature, it should be solid in nature only. Okay, V is equal to IR, where R is proportionality constant. It can be called as resistance. See here, if the terminal potential difference across this conductor is increased by increasing the potential difference of the cell. If it is a 10 volt cell, okay, you will get some amount of current. If we apply more potential difference, 20 volt cell if you connect for example, then the polarity increases here, strong electric field develop inside, so that more charge flows through this area of cross section. So, the terminal potential difference across the conductor is directly proportional to amount of flow of current in the conductor. If potential difference increases, current in the conductor is also increases, or current in the circuit increases. The proportionality is R, resistance. Resistance is independent of current in the circuit as well as that potential difference applied to the circuit. So, this is important. Proportionality constant is independent of surrounding physical quantities. Okay. Now, we will see the proportionality constant is resistance. Resistance means it is the opposition offered by a conductor for the flow of electrons within the conductor is called resistance. Resistance means opposition of flow of charge. Okay. So, the resistance is defined as the amount of opposition offered by the conductor to the flow of electrons within the conductor. Resistance, SI unit is ohm. SI unit is ohm. It can be represented with this symbol. Okay. Resistance is a scalar quantity obviously, and we would like to write a dimensional formula for this. If you want to write a dimensional formula for any physical quantity, you need one mathematical expression that I will take R is equal to V by I. Okay, current is a fundamental physical quantity, so directly its dimensional formula is A, and potential difference is not the fundamental physical quantity, so that's why we need to write a dimensional formula for potential difference. That we can write from W is equal to QV. V is equal to W by Q. So, I will write here W by Q. Next, work. Work expression is force into displacement divided by charge into ampere. We know charge is IT it. That means AT is the dimensional formula for charge. And we know force dimensional formula is mLT power minus 2. And S is L divided by T into A square. So, that is why dimensional formula becomes M power 1, L power 2, T power minus 3, A power minus 2 is the dimensional formula for resistance. Now, we will see law of resistance. See, resistance of the given conductor. For example, say this is a conductor. Resistance of this conductor is directly proportional to its length. If length increases, resistance of the conductor increases. Okay. Next, resistance decreases with increase in area of cross section. Because if area of cross section is more free electrons are available in the conductor, so that more charge can flow. More charge is flowing means more current is flowing. So obviously more flow of charge means less resistance. Why? Because resistance definition itself is that the opposition of flow of charge. If flow is more means opposition is lesser. So resistance is inversely proportional to area of cross section of the conductor. Okay. If you combine these two, you will get R proportional to L by A, and the proportionality I have to replace with some constant. That constant is, say, rho. This is called specific resistance or resistivity, L by A. So this is an expression for resistance of the conductor. Resistance depends on the dimensions. Okay, length and area of cross section. Okay. See, this is proportionality constant. It is called resistivity. Rho is specific resistance over R. Resistivity. Okay, resistance unit I know ohm. So I need to write unit for resistivity. So that I'll rearrange this equation in terms of RA by L. This resistance unit is ohm. Area unit is meter square. Length unit is meter. So resistivity SI unit is ohm meter. Okay, next, conductance. Conductance is usually denoted with letter G. Conductance is the reciprocal of resistance. Is called conductance. So unit is ohm inverse. Or it even we can call it as mho. Okay. Similarly, reciprocal of resistivity is called conductivity. Conductivity is denoted with the letter sigma. Conductivity is a reciprocal of resistivity. Okay. So unit becomes ohm inverse, meter inverse. Okay, these two things you have to remember. And resistivity, resistivity rho depends on nature of the conductor, nature of the material. That means if you see resistance expression R is equal to rho into L by A, resistance of a given conductor depends on length, area of cross section and the nature of material. For example, if you take two identical wires, one is made up of gold, another one is made up of copper. For example, these two are identical in nature. That means length same, area of cross section same, but they are made up of different material. That means these two do not have same resistance, because resistivity is different for both the wires. So that's why resistance of a given conductors depends on their dimensions as well as nature of material. Okay, we will see how this resistivity and resistance will vary with temperature. R1 is the resistance at a temperature T1 degrees centigrade, and R2 is the resistance at temperature T2 degrees centigrade. Then relation between these two is R2 is equal to R1 into 1 plus alpha into delta T. Here alpha is called temperature coefficient. Okay, alpha is positive for metals. Alpha is positive for metals. That means alpha is positive means if temperature increases, then obviously this term increases. Okay, and this we are adding for 1. That means whole value increases. that means R2 increases. If temperature increases, resistance increases for metals. And alpha is negative for semiconductors. Semiconductors. That means alpha is negative means this term becomes negative. If temperature increases, this value increases. This we are subtracting from 1. That means whole value decreases. That means R2 decreases. So in case of semiconductors, if temperature increases, resistance decreases. And alpha is almost 0 for alloys. Alloys like constantan and manganese and nichrome. These are alloys. For these alloys, alpha value is almost 0. That means alpha is 0 means 0 into anything 0. That means R1 is equal to R2. That means even temperature increases, decreases, doesn't matter. The resistance of the alloy wire remains constant. So that's why these wires can be used as a standard resistors. Okay, similarly, Rho 1 is the resistivity at temperature T1 degrees centigrade. Rho 2 is the resistivity at temperature T2 degrees centigrade. Then Rho 2 is equal to Rho 1 into 1 plus alpha delta T. Graphical representation of variation of resistivity with temperature. See, resistivity and resistance will vary in the similar manner. So if we take resistivity on the y-axis and the temperature on the x-axis, in case of metals, if temperature increases, resistivity also increases. In case of alloys, nichrome, see here the change in temperature is so large, 200, 400, 600, but resistivity is changing from only 1 to 1.1. And maybe if you change from temperature 0 to 600 degrees centigrade, it may changes from 1.2 something to 1.2 only. A large change in temperatures leads a small negligible change in resistivity. So that's why the resistivity, temperature coefficient of that particular alloys is almost 0. So resistivity changes are negligible with large change in temperatures. In case of semiconductors, if temperature increases, resistivity decreases, resistance also decreases.